Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 15. Advances in Geotechnical Engineering Practices. 15.1 Innovations in Geotechnical Engineering Materials. The field of geotechnical engineering is continuously evolving with the development of innovative materials designed to enhance the performance, sustainability, and cost efficiency of construction projects. These advancements are critical for overcoming the challenges posed by complex soil conditions, environmental concerns, and the increasing scale of infrastructure development. In this section, we explore some of the most significant innovations in geotechnical engineering materials that are reshaping the industry. 15.1.1 Geopolymers and Sustainable Materials. Geopolymers, a class of inorganic materials, have gained significant attention as sustainable alternatives to traditional Portland cement in soil stabilization and foundation applications. These materials, made from industrial byproducts like fly ash, slag, or metakaolin, owe several advantages over conventional cement, including lower carbon emissions and better resistance to chemical attack and high temperatures. Applications. Geopolymers are increasingly used for ground stabilization, soil improvement, and as a binder in various geotechnical applications. They have been successfully applied in the stabilization of expansive clays, soft soils, and waste containment structures. Advantages. Geopolymers are durable, environmentally friendly, and capable of withstanding harsh environmental conditions. They also exhibit improved strength and durability compared to traditional cement-based materials in certain applications. Future potential. As the demand for sustainable construction materials grows, geopolymers are expected to play a significant role in reducing the environmental impact of geotechnical engineering projects. 15.1.2 High-performance geosynthetics. Geosynthetics, such as geotextiles, geogrids, geomembranes, and geofoam, have revolutionized geotechnical engineering by offering lightweight, durable solutions for soil reinforcement, drainage, filtration, and environmental protection. Recent innovations in geosynthetics have enhanced their performance, allowing for more effective and versatile applications in diverse geotechnical contexts. Geogrids. Advanced geogrids made from high-strength polymer materials are now widely used for soil reinforcement and stabilization in embankments, retaining walls, and slopes. New manufacturing techniques have improved their durability and load-bearing capacity, making them suitable for use in heavy load environments such as highways, railroads, and large-scale infrastructure projects. Geomembranes. Innovations in geomembranes, particularly those made from polyethylene and polyvinyl chloride, PVC, have improved their resistance to chemicals, UV radiation, and mechanical damage. These materials are essential for applications such as landfill liners, containment structures, and waterproofing systems for foundations. Geofoam. Geofoam is a lightweight, rigid foam material used for lightweight fill-in areas with weak soils. Recent advancements have improved the thermal insulation properties of geofoam, making it an attractive option for use in geotechnical applications in cold climates or where thermal insulation is critical. Smart geosynthetics. The development of smart geosynthetics, which incorporate sensors and monitoring devices, is paving the way for real-time performance monitoring of geotechnical systems. These materials can detect changes in stress, strain, and temperature, providing engineers with valuable data for better decision-making and proactive maintenance. 15.1.3 Nano-engineered materials for soil stabilization. Nanotechnology is emerging as a promising approach for improving the properties of geotechnical materials. The use of nano-sized additives and nano-modified materials has shown potential for significantly enhancing the strength, stability, and durability of soils and other geotechnical materials. Nanoclay and nanoparticles. The addition of nanoclay particles to soils can improve their compaction characteristics, reduce permeability, and enhance shear strength. Additionally, nanosilica and nanosilicate materials are being investigated for their ability to bind soil particles at the microscopic level, leading to stronger and more durable soil structures. Nanomaterials and geopolymers. Incorporating nanoparticles into geopolymers can improve their mechanical properties, making them more effective for soil stabilization, particularly in areas with high moisture content or expansive soils. Environmental benefits. The use of nano-engineered materials can also contribute to more sustainable practices by reducing the need for chemical additives and minimizing the environmental impact of soil improvement techniques. 15.1.4 Advanced cementitious materials. Advanced cementitious materials are being developed to improve the performance and sustainability of concrete used in geotechnical applications. These materials are designed to provide superior strength, durability, and resistance to environmental degradation. High-strength concrete, high-performance concrete, HPC, which includes high-strength Portland cement and supplementary materials like silica fume, is being used in deep foundations, tunnels, and marine structures. HPC offers better resistance to shrinkage, chemical attack, and fatigue, making it ideal for high-load applications. Self-healing concrete. Self-healing concrete is a groundbreaking innovation that incorporates encapsulated healing agents, such as bacteria or polymers, that activate when cracks form in the concrete. These agents can fill cracks and restore the material's strength and integrity, reducing maintenance needs and extending the lifespan of geotechnical structures. Recycled concrete. The use of recycled aggregates and industrial byproducts, such as fly ash and slag, in concrete mixtures is gaining popularity as a sustainable approach to reduce waste and the carbon footprint of construction materials. These materials can improve the environmental performance of geotechnical infrastructure projects. 5.1.5 Bio-based and green materials. In response to the growing demand for eco-friendly construction solutions, bio-based materials are being explored for use in soil stabilization, erosion control, and foundation design. These materials, derived from renewable sources, owe the potential for sustainable and low-carbon solutions in geotechnical engineering. Biostabilization of soils. Biostabilization techniques involve the use of natural polymers such as polysaccharides, starches, and cellulose to improve soil properties. These materials can enhance the strength and stability of soils while promoting environmental sustainability. Biocementation. Microbially induced calcium carbonate precipitation (MICP) is a biocementation technique that uses bacteria to precipitate calcium carbonate in soil, thereby improving its strength and reducing permeability. This technique has shown promise for improving weak soils and preventing erosion in coastal and desert environments. Plant-based reinforcements. The use of plant-based fibers, such as jute, core, and bamboo, is an emerging trend in soil reinforcement. These fibers are biodegradable, sustainable, and capable of providing significant strength and erosion control in slope stabilization and embankment applications. 5.1.6 Smart and Adaptive Materials. Advances in smart materials are enabling geotechnical engineers to develop structures that can respond to changes in environmental conditions, loadings, and stresses. These materials have the ability to adapt their properties based on external stimuli, such as temperature, pressure, or moisture. Shape memory alloys. SMAs are materials that can return to their original shape after deformation when exposed to a specific temperature. These materials are being investigated for use in foundation systems, where they can help manage seismic movements and soil settlement by providing adaptive support. Piezoelectric materials. Piezoelectric materials generate an electric charge in response to mechanical stress. These materials are being used in geotechnical engineering to develop self-sensing foundations and embankments that can monitor structural health and detect early signs of distress. 5.1.7 Future Directions and Challenges. The continuous development of innovative materials in geotechnical engineering holds great promise for improving the performance, sustainability, and resilience of infrastructure projects. However, the integration of these materials into mainstream geotechnical practice requires thorough research, testing, and validation to ensure their effectiveness and long-term durability. Challenges. Some of the challenges facing the widespread adoption of these materials include cost, material availability, regulatory acceptance, and the need for standardized testing procedures. Additionally, the environmental impact of manufacturing these materials needs to be assessed to ensure that they contribute to sustainability goals. Future directions. The future of geotechnical engineering materials lies in the combination of sustainability, durability, and technological innovation. Continued advancements in nanotechnology, smart materials, and biological processes will play a key role in addressing the evolving challenges of geotechnical design and construction, particularly as the industry seeks to mitigate the impacts of climate change and environmental degradation. Conclusion: innovations in geotechnical engineering materials are transforming the field, enabling more sustainable, cost-effective, and resilient solutions for modern infrastructure projects. As research and development continue to advance, new materials and techniques will likely provide even more powerful tools for addressing the diverse and complex challenges faced by geotechnical engineers in the 21st century. The incorporation of these innovations will not only improve the performance of geotechnical systems, but also contribute to the creation of more sustainable and environmentally friendly construction practices. Chapter 15: Advances in Geotechnical Engineering Practices. 15.2 Smart Geotechnics. Sensors and Automation. The integration of sensors and automation into geotechnical engineering practices is ushering in a new era of smart geotechnics. This involves the use of advanced technologies to monitor and manage geotechnical systems in real time, enabling engineers to make data-driven decisions, enhance safety, optimize performance, and improve sustainability in infrastructure projects. This section explores the key advancements in smart geotechnics, with a focus on sensors, automation, and their applications in the field. 15.2.1 The role of sensors in geotechnical engineering. Sensors have become indispensable tools in modern geotechnical engineering, allowing engineers to continuously monitor various parameters such as soil pressure, temperature, moisture content, displacement, and strain. These sensors enable real-time data collection, facilitating proactive decision-making during construction and operation. Types of sensors in geotechnics. Strain gauges. Strain gauges measure the deformation or strain in a material when subjected to stress. These sensors are used to monitor the behavior of foundations, slopes, and retaining walls, helping engineers assess the load-bearing capacity and stability of structures. Piezometers. Piezometers are used to measure the pore water pressure in soils. By understanding changes in pore pressure, engineers can evaluate groundwater conditions, predict potential liquefaction events, and assess the stability of slopes and foundations in water-saturated soils. Inclinometers. Inclinometers are used to measure angular displacement or tilting in structures. These sensors are particularly valuable for monitoring the movement of retaining walls, tunnels, and slopes, helping to detect early signs of instability or deformation. Settlement sensors. These sensors measure vertical displacement or settlement in soils and structures. Settlement monitoring is crucial in assessing the long-term performance of foundations and ensuring that the settlement does not exceed acceptable limits, which could lead to structural damage. Temperature sensors. In geotechnical applications, temperature sensors are used to monitor the thermal response of soils, particularly in regions where temperature fluctuations can impact soil behavior. Temperature changes can affect soil compaction, moisture content, and even the curing process of materials like grouts or concrete. Accelerometers. These sensors detect and measure acceleration or ground motion. Accelerometers are commonly used to monitor seismic activity or the impact of vibrations during construction, providing valuable information about dynamic soil behavior and the effects of earthquakes or machinery-induced vibrations. Environmental sensors. These include sensors for measuring humidity, precipitation, and air quality. They help assess environmental conditions that may influence geotechnical processes, such as erosion, groundwater contamination, or the potential for landslides. 15.2.2 The role of automation in geotechnical engineering. Automation in geotechnical engineering refers to the use of automated systems and technologies to control and manage geotechnical processes, ranging from real-time monitoring of soil conditions to controlling construction equipment. Automation enhances the accuracy, efficiency, and safety of projects while reducing the risk of human error. Applications of automation in geotechnical engineering. Automated monitoring systems. Automated systems continuously collect data from a network of sensors embedded in the soil, foundations, or structures. These systems can detect changes in real time and send alerts to engineers when parameters exceed predefined thresholds. For instance, automated systems can monitor the stability of slopes or embankments and send immediate alerts if displacement or settlement rates become excessive. Drones and UAVs, unmanned aerial vehicles. Drones are being increasingly used for geotechnical site surveys, providing high-resolution aerial imagery and topographic data to assist in site characterization and monitoring. Drones equipped with sensors can also be used to monitor slope movement, soil erosion, or changes in groundwater levels over large areas, improving the efficiency and safety of site assessments. Robotic soil sampling. Robotic systems are now being developed to automate the process of soil sampling and testing. These robotic systems can collect samples in hard-to-reach locations, improving the efficiency of site investigations and reducing the need for manual labor. Automation of soil testing also ensures higher consistency in testing methods and results. Automated geotechnical design optimization. Software tools with embedded automation are increasingly used for designing geotechnical systems, such as foundation layouts, slope stability analysis, or ground improvement techniques. These tools use algorithms to optimize design parameters based on input data and site conditions, allowing engineers to explore multiple design options and select the most efficient and cost-effective solutions. Automated construction equipment. The use of automated machinery in construction is becoming more common, especially in geotechnical applications. Machines like excavators, bulldozers, and pile drivers equipped with automated control systems can perform tasks such as digging, compaction, and soil placement with greater precision and efficiency. These systems are often integrated with GPS technology to ensure accurate positioning and monitoring. 15.2.3 Integration of smart geotechnics in infrastructure projects. The integration of sensors and automation into geotechnical systems is revolutionizing the way engineers design, monitor, and maintain infrastructure. By providing continuous data streams and the ability to analyze large data sets in real time, smart geotechnics enhances both short-term construction activities and long-term operational performance. Smart foundations and structures. Smart foundations. Foundations equipped with embedded sensors can provide valuable data on soil conditions, load distribution, and settlement in real time. These systems allow for continuous monitoring of foundation performance, ensuring that they are functioning within acceptable limits and helping engineers detect any issues early. Smart tunnels. Advanced sensor networks and automation systems are used to monitor the construction and performance of tunnels. Sensors can measure ground movement, pressure, temperature, and deformation, ensuring that tunneling operations are proceeding safely and efficiently. Automated systems can also help control tunnel boring machines, TBMs, for optimal performance. Smart retaining walls and slopes. Retaining walls and slopes are often equipped with a combination of inclinometers, piezometers, and settlement sensors to monitor changes in slope stability, groundwater pressure, and soil behavior. Automated data collection and analysis provide engineers with a continuous assessment of the condition of retaining walls and embankments. Smart pavements. Pavement systems are being developed with embedded sensors that monitor stress, temperature, and icy loads. These systems can provide valuable feedback for pavement maintenance programs, helping engineers identify areas requiring repair or resurfacing before significant damage occurs. 15.2.4 Advantages of Smart Geotechnics. The application of sensors and automation in geotechnical engineering offers numerous advantages, including improved safety. Real-time monitoring and automated alerts allow for quick responses to potential hazards, such as slope instability, foundation failure, or excessive settlement, ensuring that corrective actions are taken before a problem escalates. Enhanced decision-making. Continuous data collection and analysis provide engineers with real-time insights into site conditions, enabling more informed decision-making throughout the project lifecycle. This leads to better design choices, construction practices, and long-term maintenance strategies. Cost savings. By optimizing construction processes and reducing the need for manual inspections and intervention, automation can lead to significant cost savings. Smart geotechnics also minimizes the risk of unexpected failures, which can result in costly repairs or delays. Increased efficiency. Automation streamlines various tasks in geotechnical engineering, such as data collection, testing, and analysis. This leads to faster decision-making and more efficient project execution, reducing the overall time and cost of construction. Sustainability. By providing detailed data on soil and structural behavior, Smart Geotechnics helps engineers design more sustainable solutions, minimizing resource use, waste, and environmental impacts over the life of the project. 15.2.5 Challenges and Future Directions. While the integration of smart geotechnics into engineering practice offers significant benefits, there are several challenges that need to be addressed. Data management. The continuous collection of vast amounts of data can overwhelm engineers and decision makers if proper systems for data management and analysis are not in place. The development of more advanced data processing tools and machine learning algorithms will be essential to manage and interpret the data efficiently. Cost. The initial cost of installing sensors and automation systems can be high. However, as the technology matures and becomes more widely adopted, costs are expected to decrease, making it more accessible for a broader range of geotechnical projects. System integration, ensuring that sensor networks, automated systems, and software tools work seamlessly together can be complex. Future developments in software interoperability and standardized communication protocols will be crucial for the success of smart geotechnics. Long-term durability. The longevity and durability of sensors and automated systems in harsh geotechnical environments are key concerns. Advances in sensor technology will need to focus on improving the robustness of devices to withstand extreme conditions such as high pressures, temperatures, and aggressive chemical environments. Conclusion: the integration of sensors and automation into geotechnical engineering, smart geotechnics, has the potential to revolutionize the industry. By providing real-time insights into soil and structural behavior, engineers can make more informed decisions, enhance safety, reduce costs, and increase the efficiency of infrastructure projects. As the technology continues to evolve, the future of geotechnical engineering will be increasingly shaped by the capabilities of sensors, automation, and data analytics, leading to smarter, safer, and more sustainable engineering solutions. Chapter 15: Advances in Geotechnical Engineering Practices. 15.3 Advances in Geotechnical Site Investigation. Geotechnical site investigation is a fundamental process in understanding the subsurface conditions of a site, and it plays a critical role in the design, construction, and maintenance of geotechnical projects. Traditional site investigation methods, such as drilling and sampling, have been enhanced over the years by new technologies and innovations, making the process more accurate, efficient, and cost-effective. This section focuses on the latest advances in geotechnical site investigation techniques, tools, and technologies. 15.3.1 Traditional Site Investigation Methods. Before delving into the new advances, it is essential to understand the conventional methods that form the foundation of site investigations. These include borehole drilling. Borehole drilling remains the primary technique for obtaining soil samples from the subsurface. The samples are analyzed to determine soil classification, strength, compaction, and other important properties. Standard penetration test, SPT. The SPT is a common in situ test where a split barrel sampler is driven into the soil, and the number of blows required to achieve a certain depth is recorded to assess the soil's resistance to penetration. Cone penetration test, CPT. This test involves the use of a cone-shaped penetrometer that is pushed into the soil at a constant rate. The resistance encountered by the cone is measured and used to determine soil properties, including stratigraphy, density, and strength. While these methods are effective, they have limitations in terms of resolution, time, cost, and accuracy. Recent advancements have provided better alternatives for site investigation. 15.3.2 Invasive and remote sensing technologies. Recent developments in non-invasive and remote sensing technologies have revolutionized the way geotechnical engineers approach site investigations. These techniques provide valuable data without the need for intrusive methods like drilling, reducing the time and cost of investigations. Ground penetrating radar (GPR). Ground penetrating radar, GPR, is a non-invasive method that uses high-frequency radar waves to investigate the subsurface. The radar waves reflect different layers in the soil, providing a profile of subsurface conditions such as soil layers, voids, and buried objects. GPR is particularly effective for detecting shallow features and is increasingly used in urban geotechnical investigations. Applications: mapping shallow subsurface features, detecting voids, locating utilities, and identifying soil heterogeneity. Advantages: provides continuous data, fast deployment, and can be used in difficult to reach areas or hazardous environments. Electrical resistivity tomography, ERT. Electrical resistivity tomography, ERT, measures the electrical resistivity of the ground by sending an electric current through the soil and measuring the voltage response. This technique helps map subsurface structures, such as faults, voids, or water-saturated layers. Applications: mapping soil composition, groundwater contamination, and identifying subsurface anomalies such as fractures or weak zones. Advantages: provides 2D or 3D images of the subsurface, allows for large area surveys, and is particularly effective in identifying soil and rock heterogeneity. Seismic refraction and reflection surveys. Seismic surveys involve measuring the travel time of seismic waves through the ground to identify subsurface structures. The seismic waves reflect or refract when they encounter different geological layers, providing information about soil properties, rock depth, and structural anomalies. Applications: identifying bedrock depth, mapping soil steepness, detecting fractures or faults, and evaluating subsurface conditions for large infrastructure projects. Advantages: provides high-resolution images of the subsurface, suitable for deep investigations, and can be used over large areas. Borehole acoustic logging. Borehole acoustic logging involves the use of sound waves to evaluate the properties of materials within a borehole. This method can be used to measure parameters such as soil steepness, porosity, and permeability. Applications: borehole stability analysis, identifying soil layering, and determining the steepness of materials. Advantages: provides high-resolution, continuous data that is useful for understanding soil behavior in situ. 15.3.3 Advances in situ testing techniques. In situ testing techniques provide real-time data on soil properties without the need for disturbing samples. These methods have seen significant advancements, improving the accuracy and range of geotechnical investigations. Dynamic Cone Penetrometer (DCP). The Dynamic Cone Penetrometer (DCP) is a portable tool used to measure the strength and steepness of soils, particularly in areas where other methods like SPT are impractical. It consists of a cone attached to a rod, which is driven into the soil using a hammer. The depth of penetration per blow is recorded to determine the soil's resistance to penetration. Applications: site characterization for road and pavement construction, mapping soil strength in granular soils, and rapid assessment of soil properties. Advantages: fast, portable, low cost, and effective for shallow investigations. Self-boring pressure meter test, SBP. The self-boring pressure meter test, SBP, is an advanced in situ test that involves inserting a probe into the soil that can expand to measure the soil's reaction to pressure. The test is used to evaluate soil strength, deformation characteristics, and stress-strain behavior under various loading conditions. Applications: characterizing cohesive soils, understanding soil-pile interactions, and evaluating lateral earth pressures. Advantages: provides detailed stress-strain behavior, high accuracy, and minimal disturbance to the soil. Wireless and remote in situ testing. The advent of wireless and remote sensing technology has made in situ testing more efficient. Wireless sensors can now transmit real-time data to a central database, allowing for continuous monitoring of geotechnical conditions. These sensors are often used in conjunction with geophysical methods and automated data collection systems, enhancing the efficiency and precision of site investigations. Applications: monitoring settlements, lateral movements, groundwater levels, and pore pressure in real time for large-scale projects. Advantages: reduced need for manual data collection, enhanced safety, and the ability to monitor remote or hazardous locations. 15.3.4 Advancements in laboratory testing. While field investigations are crucial for understanding in situ conditions, laboratory testing remains an essential part of the site investigation process. Recent advancements in laboratory techniques have enhanced the precision and range of soil property analysis. Microstructural analysis of soils. Advances in microscopy and imaging techniques, such as scanning electron microscopy, SEM, and X-ray diffraction, XRD, have allowed geotechnical engineers to study the microstructure of soils at a granular level. These methods provide insight into the composition, particle size, and pore structure of soil, which are crucial for understanding the soil's mechanical properties. Applications: evaluating soil particle morphology, analyzing soil mineralogy, and studying the behavior of soils under high-stress conditions. Advantages: improved understanding of soil behavior at the microscopic level, leading to better predictions of soil performance under load. Triaxial testing and advanced soil strength testing. Triaxial testing has seen significant advancements in terms of control systems, enabling more precise testing of soil under various conditions. New testing configurations allow for the application of multiple stress states, simulating more complex loading conditions that better reflect real-world behavior. Applications: determining the shear strength, steepness, and stress-strain behavior of soils under triaxial loading. Advantages: more accurate representation of soil behavior, improved design parameters for foundation and slope stability. 15.3.5 Integration of site investigation data. The integration of data from various site investigation methods into a cohesive, comprehensive model is becoming increasingly important. Advancements in data processing software and geospatial analysis tools allow engineers to combine results from remote sensing, in situ testing, and laboratory analysis into 3D models of the subsurface. This allows for a more complete and accurate assessment of site conditions and helps engineers make better informed design decisions. Geospatial data integration. Geospatial software tools now enable the integration of multiple data sets, such as borehole logs, CPT results, GPR scans, and seismic surveys into a unified system. This makes it easier to visualize subsurface conditions, identify potential risks, and optimize designs, applications, site characterization for large-scale projects, soil structure, interaction studies, and assessment of risk for landslides, liquefaction, and other geotechnical hazards. Advantages: improved decision-making, better communication of site conditions to stakeholders, and optimized project outcomes. Conclusion: advances in geotechnical site investigation have greatly improved the accuracy, efficiency, and scope of subsurface assessments. The use of non-invasive techniques, advanced in situ testing, wireless monitoring systems, and integration of geospatial data is transforming the way engineers approach site investigations. These innovations allow for more detailed, cost-effective, and safer geotechnical engineering solutions, enhancing the overall success of infrastructure projects and contributing to more informed, sustainable development practices. As technology continues to evolve, the future of geotechnical site investigation promises even more powerful tools for understanding and managing subsurface conditions. Chapter 15: Advances in Geotechnical Engineering Practices. 15. For the future of geotechnical engineering. The field of geotechnical engineering has undergone significant transformations over the years, with advancements in materials, methods, and technologies. Looking ahead, the future of geotechnical engineering promises further innovations that will change how we approach site investigation, design, construction, and environmental sustainability. This section explores emerging trends and potential future developments in geotechnical engineering. 15.4.1 Automation and Artificial Intelligence (AI) in geotechnical engineering. As technology continues to advance, the integration of automation and artificial intelligence (AI) is expected to revolutionize geotechnical engineering. These technologies can increase the efficiency and precision of design, construction, and monitoring processes, reducing human error and optimizing workflows. Automated data collection and analysis. With the growth of automation, geotechnical engineers are adopting AI-driven systems to analyze large amounts of site data more efficiently. AI can be used to automate the interpretation of complex geotechnical data, including soil behavior, foundation design, and seismic response. AI-powered software can analyze past project data to predict outcomes, helping engineers make better informed decisions with less manual intervention. Applications: automated site investigations, predictive geotechnical modeling, real-time monitoring of construction sites, and soil behavior prediction. Advantages: increased efficiency, reduced costs, and enhanced precision in analysis and design. Machine learning for soil behavior modeling. Machine learning algorithms are becoming increasingly popular in geotechnical engineering for modeling soil behavior. These algorithms can analyze large datasets of soil properties and performance to identify patterns and predict how soils will behave under various conditions. This can lead to more accurate modeling of soil structure interactions, especially for complex or poorly understood soils. Applications: predicting soil liquefaction potential, optimizing foundation designs, and enhancing soil property modeling. Advantages: improved predictive accuracy, cost savings, and more robust designs under uncertain conditions. 15.4.2 Advanced Materials and Sustainability. Sustainability is becoming a key focus in all engineering disciplines, including geotechnical engineering. New materials and techniques are being developed to reduce environmental impact, enhance performance, and contribute to the sustainable development of infrastructure projects. Sustainable geotechnical materials. The development and use of sustainable materials, such as recycled aggregates, bio-based polymers, and geopolymers, are gaining attention in geotechnical engineering. These materials owe an eco-friendly alternative to traditional geotechnical materials while maintaining or improving their strength and durability. Applications: eco-friendly foundations, soil stabilization using sustainable additives, and the use of recycled materials for ground improvement. Advantages: reduced environmental footprint, lower carbon emissions, and increased sustainability of construction projects. Carbon sequestration through geotechnical solutions. Carbon sequestration, or the long-term storage of carbon dioxide, CO2, is becoming a focus of research in the geotechnical field. Methods such as soil carbonation, the use of waste byproducts in soil stabilization, and the development of geotechnical solutions for carbon capture are areas of active exploration. Geotechnical engineering could play a key role in helping to combat climate change by sequestering CO2 in the ground. Applications: carbon sequestration in construction materials, enhancing natural carbon storage in soils, and developing CO2 capture techniques through soil improvement. Advantages: mitigation of climate change, reduction of greenhouse gases, and support for global sustainability goals. 15.4.3 Smart Infrastructure and Monitoring Systems. The integration of smart sensors, IT, Internet of Things, technologies, and real-time data analytics is transforming how geotechnical engineers approach the monitoring and maintenance of infrastructure. By embedding sensors into soil, foundation systems, and other critical infrastructure components, engineers can monitor their performance continuously and make real-time decisions. Smart foundations and structures. Smart foundations embedded with sensors can measure parameters such as settlement, displacement, temperature, and moisture content. This real-time data enables proactive maintenance and design adjustments during the construction phase or throughout the lifespan of a structure. For example, smart foundations can monitor the health of buildings, bridges, and dams, alerting engineers to potential issues before they become critical. Applications: real-time monitoring of settlements, stress/strain behavior, foundation movement, and environmental conditions. Advantages: increased safety, reduced maintenance costs, longer service life, and proactive detection of potential problems. Autonomous construction technologies. The use of autonomous equipment, such as drones, robotic excavators, and automated machinery, is poised to change construction practices. These technologies can be used for geotechnical site surveys, excavation, material handling, and even the installation of geotechnical elements such as deep foundations and soil stabilization systems. Applications: site preparation, surveying, geotechnical construction, and remote monitoring of geotechnical sites. Advantages: increased efficiency, enhanced safety, and reduced human labor. Requirements: 15.4.4 Advanced computational methods and simulation. As computational power continues to increase, more sophisticated and accurate simulations of geotechnical systems will be possible. Advances in computational modeling will allow engineers to simulate complex soil structure interactions, groundwater flow, and the impact of dynamic loading on foundations with unprecedented precision. Multi-scale modeling. Multi-scale modeling techniques are becoming more common in geotechnical engineering, which allow engineers to simulate phenomena from the molecular level to the macro scale of engineering systems. This technique is particularly useful for studying the behavior of materials under extreme conditions or in environments where detailed analysis is necessary, such as in permafrost, expansive soils, or during seismic events. Applications: simulating soil structure interaction, understanding complex geological formations, and analyzing dynamic loads on infrastructure. Advantages: more detailed and accurate models, enabling better predictions of real-world behavior and optimized design. Integrated simulation platforms. The development of integrated simulation platforms, where various geotechnical processes such as soil behavior, groundwater flow, and seismic response are modeled together, is an exciting prospect. These platforms can combine data from field investigations, laboratory tests, and real-time monitoring, allowing engineers to create a unified model that provides insights into how the entire system behaves under various conditions. Applications: comprehensive site analysis, integrated modeling of complex geotechnical systems, and improved risk assessment. Advantages: better understanding of the interactions between different geotechnical components, more accurate predictions, and enhanced decision making. 15.4.5 Collaboration and interdisciplinary approaches. The future of geotechnical engineering will increasingly require collaboration across multiple disciplines. As infrastructure projects become more complex, geotechnical engineers will need to work closely with structural, environmental, and civil engineers, as well as urban planners, architects, and environmental scientists to design sustainable and resilient systems. Integrated Project Delivery (IPD). Integrated Project Delivery (IPD) is an approach that emphasizes collaboration and sharing of resources, expertise, and risks among all project stakeholders. This model can lead to more efficient and sustainable geotechnical engineering solutions by fostering a holistic approach to design, construction, and maintenance. Applications: large-scale infrastructure projects, urban planning, and environmentally sensitive construction projects. Advantages: improved collaboration, reduced project delays, enhanced cost, efficiency, and more innovative solutions. Conclusion: the future of geotechnical engineering holds great promise. With the ongoing developments in automation, AI, sustainable materials, smart technologies, and advanced computational methods, geotechnical engineers are positioned to address the challenges of a rapidly changing world. These advances will lead to more efficient, resilient, and sustainable infrastructure solutions, helping to mitigate environmental impacts and support the development of smart, safe, and sustainable cities. As the industry continues to evolve, geotechnical engineers will play an increasingly vital role in shaping the built environment, contributing to a more sustainable and adaptable future for generations to come. Chapter 16: Ethical, Legal, and Professional Aspects of Geotechnical Engineering. 16.1 Professional Ethics in Geotechnical Practice. Professional ethics are fundamental to the practice of geotechnical engineering. Engineers are entrusted with public safety, environmental protection, and the integrity of infrastructure projects. Therefore, adhering to a strong ethical framework is crucial for ensuring that geotechnical engineers meet their responsibilities and obligations in a manner that upholds public trust and serves society's needs. This section explores the key principles of professional ethics in geotechnical engineering, the challenges engineers face, and the ways in which ethical considerations influence practice. 16.1.1 Core Principles of Ethical Practice. The ethical practice of geotechnical engineering is built upon several core principles that guide engineers in their professional conduct. 1. Public safety and welfare. Geotechnical engineers have a paramount responsibility to protect the public from harm. This involves ensuring that designs, constructions, and site assessments meet safety standards and are free from potential hazards. Engineers must act in a manner that safeguards human life, property, and the environment. Responsibilities: ensuring that the safety and well-being of communities are prioritized, especially in areas such as foundation design, slope stability, and earthquake resilience. Ethical decision: deciding on design changes that prioritize safety over cost, cutting, or expedience. 2. Integrity and honesty. Engineers must provide honest, accurate, and unbiased information in all aspects of their work. Integrity is essential when presenting test results, evaluations, or when making recommendations for geotechnical solutions. Responsibilities: avoiding any manipulation or distortion of data, being transparent about risks, and presenting clear findings even if they may be unfavorable or difficult for stakeholders. Ethical decision: reporting negative findings, such as poor soil conditions, without bias or pressure from clients. 3. Competence and expertise. Geotechnical engineers are expected to maintain and improve their skills throughout their careers. By adhering to ethical standards, engineers ensure that they only take on projects for which they are adequately qualified, and they seek assistance when needed. Responsibilities: continuous professional development through education and practical experience, ensuring qualifications and certifications are current, and working within one's area of expertise. Ethical decision: not accepting projects or tasks that exceed one's knowledge and competence, and consulting with specialists when required. 4. Environmental responsibility. Geotechnical engineers are responsible for understanding and minimizing the environmental impacts of their projects. This includes considering sustainable practices in soil stabilization, waste disposal, and site development. Responsibilities: minimizing environmental degradation by adhering to best practices in sustainability, reducing waste, and conserving natural resources. Ethical decision, opting for environmentally sustainable solutions even if they might incur additional costs or take longer to implement. 5. Professionalism and accountability. Geotechnical engineers must maintain a high standard of professionalism in their interactions with clients, stakeholders, and colleagues. Accountability is a key aspect of this, as engineers must take responsibility for their actions, decisions, and the outcomes of their work. Responsibilities: keeping clients informed, addressing conflicts of interest, and taking responsibility for the outcomes of the work. Ethical decision: acknowledging mistakes and rectifying them, whether on a technical issue or a project management matter, and ensuring that work is completed as promised. 16.1.2 Ethical challenges in geotechnical engineering. Geotechnical engineers face a variety of ethical challenges during their careers, many of which require a careful balance between competing interests. Some of the key challenges include: 1. Conflicts of interest. Conflicts of interest can arise when the interests of a client, employer, or other parties interfere with an engineer's impartial judgment. For example, an engineer might feel pressured to overlook risks in order to meet deadlines or save costs. Challenge: balancing professional responsibilities with the interests of clients, stakeholders, and contractors. Solution: transparency and disclosure of potential conflicts and recusal from decisions where impartiality could be compromised. 2. Pressure to compromise standards. In some cases, engineers may face pressure to compromise safety, quality, or ethics to meet project timelines or reduce costs. This could include overlooking unfavorable geotechnical findings or reducing safety margins in design. Challenge: the ethical dilemma between satisfying clients' demands and adhering to professional safety and engineering standards. Solution: standing firm on professional principles, even when faced with opposition, and refusing to compromise on safety and quality standards. 3. Environmental impacts. Geotechnical engineers may encounter situations where they are asked to design solutions that could have significant negative environmental consequences, such as disturbing sensitive ecosystems or creating long-term environmental hazards. Challenge: navigating the ethical dilemma between development needs and environmental protection. Solution: advocating for and implementing sustainable practices and solutions that minimize adverse environmental impacts. 4. Transparency and reporting. Engineers must sometimes confront situations where data is incomplete, misleading, or problematic. The ethical course of action is to report findings truthfully, even if this may delay the project or result in unforeseen costs. Challenge: the decision to disclose information that could potentially ECTA project's viability. Solution: always reporting findings honestly, prioritizing public safety and welfare, and ensuring transparency throughout the project lifecycle. 16.1.3 Ethical codes and professional organizations. The geotechnical engineering profession is governed by ethical codes and standards set by professional organizations. These organizations provide guidelines that help engineers navigate ethical dilemmas and promote high standards of practice. Code of Ethics by professional bodies. American Society of Civil Engineers, The ASC Code of Ethics outlines the ethical responsibilities of engineers to the public, clients, and profession. It includes provisions for honesty, fairness, transparency, and respect for human rights. Institution of Civil Engineers. ICE's Code of Professional Conduct provides a framework for engineers to practice in an ethical manner, emphasizing the importance of integrity, professional development, and environmental responsibility. International Society for Soil Mechanics and Geotechnical Engineering. ISSMG promotes ethical principles for geotechnical engineers, highlighting the need for competence, ethical decision-making, and the protection of human and environmental interests. By adhering to these codes of ethics, engineers can ensure that their practice is aligned with the broader goals of public safety, sustainability, and social responsibility. 16.1.4 Case Studies in Ethical Geotechnical Practice. The application of professional ethics can often be illustrated through real-world case studies that highlight how ethical decisions shape the outcomes of geotechnical projects. Below are a few examples of scenarios where ethical considerations played a critical role. Case Study 1. Foundation failure and transparency. In a high-rise building project, geotechnical engineers discovered issues with the soil-bearing capacity that could result in settlement problems. Despite pressure to continue with construction, the engineers reported the findings to the client, which led to a redesign of the foundation. The ethical decision to prioritize safety prevented a costly and dangerous failure. Case Study 2. Environmental concerns in a waste disposal project. An engineer working on a landfill project faced the dilemma of recommending a cost-effective solution that involved minimal environmental monitoring. However, recognizing the potential long-term environmental hazards, the engineer advocated for a more thorough monitoring system, ensuring that the project complied with environmental protection standards and ultimately preserving local ecosystems. Conclusion: professional ethics in geotechnical engineering are foundational to the integrity of the profession and the safety of the public. Engineers must navigate complex ethical dilemmas, balancing the demands of clients with their responsibility to uphold safety, sustainability, and environmental protection. By adhering to ethical codes, engaging in continuous professional development, and making decisions based on transparency and honesty, geotechnical engineers contribute positively to society, ensuring the safety and resilience of infrastructure projects for future generations. Chapter 16. Ethical, legal, and professional aspects of geotechnical engineering. 16.2 Legal considerations in geotechnical projects. Geotechnical engineering involves significant legal considerations, as it directly impacts public safety, environmental sustainability, and the economic feasibility of projects. Legal issues can arise throughout the life cycle of geotechnical projects, from site investigation and design to construction and operation. Understanding the legal framework within which geotechnical engineers work is crucial for minimizing risks, ensuring compliance, and protecting both the engineer and the public. This section explores the key legal considerations that geotechnical engineers must be aware of in their professional practice. 16.2.1 Legal liabilities in geotechnical engineering. Geotechnical engineers bear legal responsibilities for their work, especially when it comes to the safety and stability of structures built upon soil and rock. Legal liabilities can arise from errors, omissions, or negligence in various stages of a project. 1. Negligence and professional liability. Negligence. Geotechnical engineers can be held liable for negligence if they fail to exercise the level of care and expertise that a reasonable professional would in similar circumstances. This can include errors in soil analysis and proper design, recommendations, or failure to detect subsurface hazards. Professional liability. Engineers can face legal action if their professional judgment or work leads to harm, including personal injury or property damage. If a geotechnical engineer's decisions directly contribute to structural failures, landslides, or other safety hazards, they may be held responsible. 2. Breach of contract. Contracts between geotechnical engineers, clients, and other project stakeholders outline the scope of work, timelines, fees, and deliverables. A breach of contract occurs when the engineer fails to fulfill these obligations, either by not completing the work or delivering work that does not meet the agreed-upon standards. Legal recourse. Clients may sue for damages if the geotechnical engineer fails to meet contractual obligations. Engineers may need to demonstrate that they met industry standards and acted within the scope of their competence to avoid liability. 3. Product liability. Geotechnical engineers involved in selecting materials or equipment for a project may be held liable if the materials or methods they recommend are found to be faulty or dangerous. In this case, the engineer may be held responsible for damages resulting from the failure of these materials or designs. 16.2.2 Regulatory compliance and standards. Geotechnical engineers must adhere to a wide range of local, national, and international regulations, standards, and codes. These regulations are designed to ensure the safety, reliability, and sustainability of geotechnical projects. Non-compliance with these regulations can result in legal and financial consequences for both the engineer and the project owner. 1. Local and national building codes. Building codes are designed to set minimum standards for construction and infrastructure. Geotechnical engineers must be familiar with and comply with relevant building codes that pertain to foundation design, slope stability, seismic analysis, and soil mechanics. Example, in the United States, the International Building Code, IBC, provides guidelines on how to design structures safely, including the assessment of foundation soil properties and seismic design considerations. Similarly, many countries have national standards, e.g., Eurocode in Europe, AS 1170 in Australia, that govern geotechnical practices. 2. Environmental regulations. Geotechnical engineers must also be aware of environmental laws that govern construction and development projects. These may include regulations on groundwater, contamination, soil erosion, and habitat disruption. Failure to comply with environmental regulations can lead to fines, project delays, and reputational damage. Example, the Clean Water Act and the National Environmental Policy Act, NEPA, in the United States require that projects assess potential environmental impacts, including those related to geotechnical work, such as site contamination or potential EX on water resources. 3. Health and safety regulations. Geotechnical engineers are legally responsible for ensuring that their work complies with occupational health and safety regulations. This includes assessing potential risks for workers involved in site investigations, drilling, or construction. Example: the Occupational Safety and Health Administration, OSHA, in the U.S., establishes regulations that engineers must follow to ensure the safety of personnel on construction sites, such as guidelines for excavation safety, risk assessments, and handling hazardous materials. 16.2.3 Environmental Impact and Permitting. Environmental regulations play a critical role in geotechnical engineering projects. In many jurisdictions, engineers must obtain permits before proceeding with certain activities, particularly when working in environmentally sensitive areas or when a project may cause disruption to the surrounding environment. 1. Environmental Impact Assessments (EIA). Many large-scale geotechnical projects require an Environmental Impact Assessment (EIA) to evaluate the potential EX on the environment. This process helps to identify possible environmental risks such as soil erosion, contamination, or habitat loss, and to develop mitigation strategies. Legal requirement. An EIA is often mandated by law before projects such as large dams, highways, or industrial complexes can proceed. Failure to conduct a proper EIA may result in legal challenges or halted construction. 2. Permitting process. Geotechnical engineers must often work with regulatory authorities to obtain permits for their work. For example, permits may be required for soil borings, excavation activities, or the installation of geotechnical monitoring equipment. Legal requirement. These permits are issued by local or national authorities and are designed to ensure that geotechnical work does not harm public safety or the environment. Engineers must ensure they comply with these requirements to avoid delays, fines, or work stoppages. 16.2.4 Contractual Agreements and Dispute Resolution. Geotechnical projects are typically governed by contracts that define the rights and responsibilities of all parties involved. It is essential for geotechnical engineers to understand the legal implications of contracts and be prepared to address any potential disputes. 1. Standard contract forms. In many countries, standard contract forms exist to streamline the legal process for geotechnical projects. These contracts typically outline the scope of work, timelines, fees, and dispute resolution procedures. Example: in the U.S., the American Society of Civil Engineers, ASCE, provides standard contract templates for geotechnical engineers that can help define the responsibilities of both parties and clarify the terms of engagement. 2. Dispute resolution mechanisms. Disputes can arise in any phase of a geotechnical project, whether regarding payment, project delays, or technical disagreements. It is essential that contracts clearly outline dispute resolution mechanisms, such as arbitration or mediation, to avoid prolonged litigation. Example: if there is a disagreement about the quality of the geotechnical investigation or if soil conditions are not accurately assessed, dispute resolution mechanisms such as arbitration can be employed to resolve the matter without going to court. 16.2.5 Insurance and Risk Management. Geotechnical engineers must protect themselves and their clients by securing appropriate insurance coverage and managing potential risks associated with their work. Insurance helps mitigate the financial consequences of potential liabilities. 1. Professional liability insurance. Professional liability insurance, also known as errors and omissions insurance, protects geotechnical engineers from claims arising due to negligence, errors, or omissions in their work. This type of insurance is vital in shielding engineers from the financial burden of lawsuits. Importance: in the event of a failure, such as a foundation collapse or slope failure, professional liability insurance can cover legal defense costs and any damages resulting from the engineer's work. 2. Risk management. Geotechnical engineers must also employ active risk management strategies throughout a project's life cycle. This includes conducting thorough site investigations, using appropriate testing methods, and ensuring that designs comply with legal and safety standards to reduce the likelihood of failure. Importance: proper risk management minimizes the potential for accidents or lawsuits, ensuring a smooth project delivery process and reducing legal exposure. Conclusion: legal considerations are a crucial aspect of geotechnical engineering practice. Engineers must ensure compliance with regulations, understand their professional liabilities, and be proactive in managing risks. By familiarizing themselves with legal requirements, including contracts, permitting, environmental laws, and professional standards, geotechnical engineers can mitigate legal risks, protect themselves from liabilities, and contribute to successful, safe, and legally compliant projects. Chapter 16: Ethical, Legal, and Professional Aspects of Geotechnical Engineering. 16.3 Standards, Codes, and Regulations. Geotechnical engineering is governed by a wide range of standards, codes, and regulations designed to ensure the safety, integrity, and environmental sustainability of engineering projects. These frameworks are essential in guiding engineers to perform their duties with competence, ensuring that their designs and practices meet societal needs while mitigating risks. This section explores the key standards, codes, and regulations that geotechnical engineers must adhere to throughout the course of their professional practice. 16.3.1 National and International Standards. National and international standards form the foundation of geotechnical engineering practices, helping engineers maintain consistency and quality across projects. These standards are developed by specialized organizations, often in collaboration with governmental and industry bodies, and are periodically updated to reflect advancements in research and technology. 1. International Standards. ISO, International Organization for Standardization. ISO standards are widely recognized globally and provide guidelines for various aspects of engineering, including soil testing, site investigation, and foundation design. ISO standards like ISO 22475, Geotechnical Investigation and Testing, and ISO 14688, Geotechnical Investigation and Soil Testing, help ensure uniform practices in soil testing and analysis across different regions. Eurocode. In Europe, the Eurocode standards are a set of rules for the design of buildings and civil engineering works, which include specific geotechnical provisions. The Eurocode 7 Geotechnical Design covers topics like soil properties, foundation design, slope stability, and ground improvement techniques. This code serves as a comprehensive guide to geotechnical engineering in Europe, helping ensure uniformity and safety in design practices. 2. National standards. Each country typically has its own set of geotechnical engineering standards that align with local conditions, climate, and regulatory requirements. Some examples include ASTM, American Society for Testing and Materials in the United States, ASTM, provides a wide range of standards covering soil testing, geotechnical analysis, and construction practices. ASTM D1586, Standard Test Method for Penetration Test and Split Barrel Sampling of Soils, and ASTM D2487, Standard Practice for Classification of Soils for Engineering Purposes, are widely used in geotechnical investigations. BSI, British Standards Institution in the UK, BSI standards like BS 5930, Code of Practice for Site Investigations, and BS 8004, Code of Practice for Foundations, provide detailed guidance for geotechnical investigation and foundation design. Australian standards. AS in Australia. The AS 1289 series covers soil testing methods, while AS 5100 focuses on the design of bridges, including geotechnical considerations for foundation design. These national standards not only ensure the quality and safety of projects, but also help harmonize practices across different regions. 16.3.2 Geotechnical Design Codes. Geotechnical design codes provide specific design procedures, calculation methods, and requirements that engineers must follow to ensure the stability and safety of structures. These codes offer standardized approaches to challenges such as foundation design, slope stability, and soil structure interaction. 1. Foundation Design Codes, U.S. Codes. In the United States, the OSHTO LRFD Bridge Design Specifications provide geotechnical design guidelines for foundations related to bridge construction. For building foundations, the IBC, International Building Code, includes geotechnical provisions that ensure structures are built on stable and appropriately designed foundations. Eurocode 7. Eurocode 7 provides detailed guidelines for the design of foundations, covering aspects such as bearing capacity, settlement, and slope stability. It includes design methods for shallow and deep foundations and outlines, geotechnical analysis methods. 2. Seismic Design Codes. Geotechnical engineers must also comply with seismic design codes that specify how to design foundations and structures to withstand earthquake forces. Some of these codes include NHRP, National Earthquake Hazards Reduction Program in the U.S., NERP, provides guidelines for earthquake-resistant design, including soil structure, interaction, and seismic ground motions. Eurocode 8. This Eurocode provides seismic design provisions for geotechnical aspects of structures, including site classification, seismic hazard assessment, and the impact of seismic loading on foundations. 3. Slope Stability and Ground Improvement Codes, ASTM and BS Codes. These include guidelines for analyzing and designing slopes and embankments. For example, ASTM D5806 provides a standard guide for slope stability analysis, while BS 8002 provides design principles for earth-retaining structures and slopes. 16.3.3 Environmental and Safety Regulations. Geotechnical engineers must consider environmental and safety regulations to minimize risks to public health, safety, and the environment. These regulations often require comprehensive risk assessments, site investigations, and sustainable design practices. 1. Environmental Impact Assessment (EIA) regulations. Environmental regulations are critical to ensuring that geotechnical projects do not cause irreversible harm to the environment. An EIA is typically required for large infrastructure projects that may impact the environment, such as the construction of dams, tunnels, highways, and bridges. The EIA evaluates the potential effects of a project on soil, water, air quality, and biodiversity, and includes mitigation strategies. U.S. NEPA, National Environmental Policy Act in the U.S., NEPA mandates the preparation of an EIA for major federal projects that could have a significant impact on the environment. Geotechnical engineers may be called upon to assess soil contamination, groundwater flow, and other factors that could affect the environment. EU directives. The European Union has established directives to guide environmental assessments, such as the EIA Directive, Directive 2011/92/EU, which sets out the rules for assessing the environmental impact of public and private projects. 2. Health and safety regulations. Geotechnical engineers must ensure that their work adheres to local occupational health and safety regulations, which are designed to protect workers and the public. These regulations cover areas such as excavation safety, hazardous material handling, and structural stability during construction. OSHA standards. Occupational Safety and Health Administration in the U.S. OSHA regulations govern construction site safety, including the safe design and execution of geotechnical fieldwork. The regulations address issues such as trenching, excavation, and the safe operation of drilling equipment. European safety regulations. In Europe, regulations like the EU Framework Directive 89/391/EC on health and safety at work provide guidelines for ensuring worker safety on construction sites, including those involving geotechnical operations. 16.3.4 Ethical Standards in Geotechnical Engineering. In addition to legal and regulatory standards, geotechnical engineers must adhere to ethical standards that prioritize public safety, environmental sustainability, and professional integrity. Ethical guidelines are often outlined by professional bodies such as ASC, American Society of Civil Engineers. The ASC Code of Ethics stresses the responsibility of engineers to hold paramount the safety, health, and welfare of the public. Geotechnical engineers must act with honesty, fairness, and impartiality in all their professional dealings. Geotechnical Engineers Association, GA. The GA and similar organizations provide ethical frameworks for geotechnical engineers, emphasizing the importance of ethical decision-making, client confidentiality, and the responsible use of resources. Ethical considerations also include avoiding conflicts of interest, ensuring transparency in reporting findings, and prioritizing sustainable design solutions. 16.3.5 International Harmonization and Best Practices. Many countries and organizations are working toward the international harmonization of geotechnical standards. This can help ensure consistent practices across borders and make it easier for engineers to collaborate on international projects. International Society for Soil Mechanics and Geotechnical Engineering. ISSMG promotes the sharing of knowledge and best practices in geotechnical engineering globally. The Society supports the development of international standards and guides for various aspects of geotechnical practice, including site investigation, soil testing, and foundation design. World Bank and UN projects. International institutions like the World Bank and the United Nations have developed their own geotechnical standards and practices, particularly for projects in developing countries. These guidelines help ensure that projects meet international quality standards while promoting sustainable development. Conclusion: adhering to standards, codes, and regulations is critical for geotechnical engineers to ensure the safety, quality, and environmental sustainability of their projects. These frameworks provide guidelines for every aspect of geotechnical practice, from design and analysis to construction and environmental protection. Geotechnical engineers must remain updated on the relevant standards, codes, and regulations in their region and internationally to avoid legal and ethical pitfalls and contribute to the advancement of the field. Chapter 16. Ethical, Legal, and Professional Aspects of Geotechnical Engineering. 16.4 The role of geotechnical engineers in society. Geotechnical engineers play a critical and multifaceted role in society, contributing to the safety, stability, and sustainability of infrastructure, as well as ensuring the long-term viability of construction projects. Their expertise in understanding soil, rock, and groundwater behavior is essential for the design and construction of nearly all civil engineering projects, including buildings, roads, bridges, dams, and tunnels. This section explores the broader responsibilities of geotechnical engineers and their profound impact on the community, economy, and environment. 16.4.1 Ensuring public safety and welfare. The primary responsibility of geotechnical engineers is to safeguard the public by ensuring that structures built on or in the ground are stable and safe. Geotechnical engineers assess soil and rock conditions to design foundations and other earth structures that can withstand various forces, including the weight of the structure, environmental loads, and natural disasters such as earthquakes, floods, and landslides. Without the expertise of geotechnical engineers, there would be a significant risk of structural failures, which could lead to catastrophic consequences, including loss of life and property damage. Key responsibilities. Foundation design. Geotechnical engineers design foundations that ensure buildings, bridges, and other structures remain stable over time. Slope stability and landslide prevention. By understanding the characteristics of soil and rock masses, geotechnical engineers assess and mitigate the risk of slope failures and landslides, protecting both infrastructure and human lives. Seismic safety. In earthquake-prone areas, geotechnical engineers play a vital role in assessing soil behavior under seismic conditions and designing earthquake-resistant foundations and structures. 16.4.2 Contribution to Sustainable Development. Geotechnical engineers help ensure that the built environment is resilient and sustainable by implementing techniques that minimize the impact of construction on the environment and maximize the durability and efficiency of structures. They play a crucial role in addressing issues like land degradation, resource depletion, and climate change by incorporating sustainability principles into their designs. Key areas of contribution: sustainable foundation practices. Geotechnical engineers use their knowledge of soil mechanics and material science to design foundations that are not only stable, but also efficient in terms of resource usage, minimizing energy consumption and reducing the need for excessive materials. Environmental protection. Through techniques such as soil stabilization, erosion control, and groundwater management, geotechnical engineers contribute to protecting the environment and reducing the impact of construction activities on natural resources. Geotechnical engineering in green infrastructure. Geotechnical engineers work with green infrastructure projects such as sustainable urban drainage systems, SUDs, green roofs, and permeable pavements that reduce environmental impacts and promote long-term ecological balance. 16.4.3 Advancing Knowledge and Innovation. Geotechnical engineers are at the forefront of advancing scientific knowledge in the field of soil mechanics, geophysics, and foundation design. Their contributions to research and development help to refine existing practices and introduce new methods for solving complex engineering challenges. This is especially important as urbanization and technological advancements create increasingly complex geotechnical problems. Key contributions: innovations in ground improvement. Geotechnical engineers are instrumental in developing innovative techniques like soil grouting, deep soil mixing, and geosynthetics that improve ground conditions for construction purposes, enabling the development of structures in challenging environments. Improve testing and analysis methods. By advancing the techniques and technology for soil testing and site investigation, geotechnical engineers provide more accurate and reliable data, allowing for more efficient and cost-effective designs. Sustainability research. Geotechnical engineers are involved in researching methods to reduce carbon footprints in construction, such as reducing the environmental impact of foundation systems and incorporating alternative materials and techniques. 16.4.4 Addressing global and local challenges. Geotechnical engineers face a wide range of challenges, both at the local and global level, in dealing with issues such as rapid urbanization, climate change, and resource management. Their role in addressing these challenges is more critical than ever as the world confronts population growth, environmental degradation, and increased demand for infrastructure. Key global and local challenges. Urbanization. As cities grow rapidly, geotechnical engineers are called upon to design infrastructure in increasingly congested and complex environments, including managing ground conditions in heavily built-up areas. Climate change. With the increasing occurrence of extreme weather events, such as floods, storms, and droughts, geotechnical engineers must adapt their designs to account for the changing landscape. This includes addressing issues related to soil erosion, groundwater recharge, and flood risk mitigation. Natural disasters. Geotechnical engineers play a key role in earthquake engineering, flood control, and landslide prevention, contributing to disaster preparedness and recovery efforts in areas vulnerable to natural disasters. 6.4.5 Professional integrity and ethical responsibility. As professionals, geotechnical engineers are expected to uphold the highest ethical standards. Their decisions impact public safety, environmental health, and the financial well-being of stakeholders. It is essential that geotechnical engineers act with integrity, transparency, and responsibility, balancing the needs of their clients with the broader needs of society. Key ethical responsibilities. Public trust. Geotechnical engineers must prioritize the welfare of the public, ensuring that their designs and recommendations are made with safety, reliability, and environmental considerations at the forefront. Integrity in reporting. Engineers must provide accurate, unbiased information in their reports and analyses, regardless of external pressures from clients or other stakeholders. Accountability. Geotechnical engineers must take responsibility for their designs and decisions, acknowledging any shortcomings or mistakes and taking corrective action when necessary. 6.4.6 The geotechnical engineer as a leader and educator. In addition to their technical expertise, geotechnical engineers often serve as leaders and educators in the engineering community. They mentor younger engineers, collaborate with other professionals, and contribute to the development of the field through teaching, publishing, and presenting at conferences. By sharing their knowledge and experience, they help elevate the profession and inspire future generations of engineers to solve the world's most pressing problems. Key roles, mentorship and leadership. Experienced geotechnical engineers often serve as mentors, guiding younger professionals through complex projects and helping them develop their skills and knowledge. Academic contributions. Many geotechnical engineers contribute to academia by teaching courses, conducting research, and publishing papers that expand the body of knowledge in the field. Professional organizations. Geotechnical engineers play a key role in professional organizations such as the ASC and ISSMGE, where they contribute to the development of industry standards, codes, and best practices. Conclusion. Geotechnical engineers play a crucial role in society by ensuring that infrastructure is built safely, efficiently, and sustainably. Their work impacts every aspect of modern life, from the foundations of buildings to the roads we drive on and the bridges we cross. As trusted professionals, geotechnical engineers must navigate complex ethical, legal, and environmental challenges while upholding the highest standards of practice and contributing to the well-being of society. Their role will continue to evolve as the world faces new challenges, but their contribution to building a safer, more sustainable future remains as critical as ever. Thank you for taking the time to watch this video lecture on the Triune Biblical University Global Extension USA channel. Please remember to like, share, subscribe, and leave a comment to help us bring more educational content your way.